Let's continue the worked examples on lenses. Remember that lenses are a transparent material and the light rays will refract through them. So the light rays that you're drawing must go through the lens, unlike a mirror where the light is reflected off of it. So refer to the 3 rules in your notes about the light ray rules for mirrors, and let's get to it. Grab your ruler. First light ray that we're going to draw, leaving the object towards this convex lens, is going to travel parallel to the axis to the center of the lens, and then will refract through the focal point. The next light ray rule that we're going to use, we can't use the one through the focus on the near side and parallel to the axis because you see that light ray will miss that lens. So we have to use the 3rd rule, which is light rays traveling through the center of the lens will travel through unaffected. Where those 2 light rays meet or converge, that's where the image will be found. So all the way over on the right side of your page here, we're going to see the image. You can draw that up to the principal axis. And again, the light rays left the top of the object, so they must be at the top of the image on the far side. The type of image is a real image because those light rays are converging. The orientation is inverted compared to the object. It's pointing in the opposite direction. And the size, as you can see, is larger. If we go to use the mirror and lens equation, we can calculate what is the distance to the image and what is the height of the image as well. So first step, to solve for di, we're going to take the 1 over f equals 1 over di plus 1 over do equation. Solving for di, I'm going to subtract 1 over do from both sides and then take the inverse. So di will equal the inverse of 1 over f, which is 14 to the negative 1, and we're going to subtract the do, the inverse of it, which is 20 to the negative 1. Take the inverse of all of that, and you're left with an answer of 46.7 centimeters. Once you know that, so that's our first step, once you know that, we can go and find the height of the image. So from our equation, hi over ho equals negative di over do. We're going to multiply both sides by ho, so that comes up to the top over there. So hi is equal to negative di times ho over do. So we can put that negative up front. The distance to the image we just found is 46.7 centimeters. Height of the object is 12. Distance to the object is 20. And if you type that in, you'll find the height of the image is negative 28 centimeters. So you can see that value there is much greater than the height of the object over there. And therefore, it's magnified. Okay, worked example number 10. You'll see the object is inside the focal point on the convex lens, and this is where we have the magnifying glass situation. So this is the only example that you'll see a virtual image being formed with a convex lens. Same rules apply, you just have to think a little bit about where the light is heading and where it might appear to be coming from. So line up your ruler parallel to the axis, and your first ray traveling parallel to the axis to the center of the lens, and then will bend through the focal point. Now leave your ruler where it is, and I want you to follow that back with a dashed line on the far side. That's where your eye would think that light is coming from. So light rays traveling off up to the right there. Next rule, I'm going to use the light rays traveling through the center of the lens, travel through unaffected. So straight through the center. And again, leave your ruler where it is, and then draw your dashed lines back on the left side. So you'll see those 2 light rays leaving the lens are diverging, which means if your eye was on that side, it would think that the light was coming together from the far side. So we'll draw in where those light rays appear to be coming together. We'll draw in our image there. And that's exactly the situation you're seeing with the magnifying glass. The type of image is a virtual image because those light rays are diverging, so the light's not actually starting where the image is, it just appears to be coming from there. The orientation, if you compare the image, it is upright compared to the object, and it is obviously larger. Now, if you use the mirror and lens equations, I'll just write the answers down. I hope by this point you can sort the algebra out on your own. The distance to the image you'd see would be negative 13.3 centimeters. And that just tells you that the image is on the same side of the lens as the object. The focal length, if you calculate it, it will come out to 8 centimeters. Next example, same rules apply. Light rays from the top of the object will travel parallel to the axis and then through the focal point. Light rays through the center of the lens will travel straight through. Light rays through the focal point to the lens will then travel parallel to the axis. You'll see if you draw it perfectly, all three of those light rays should end up at exactly the same spot. So your image will be found right here. Again, notice you only need 2 of the light rays to be satisfied, but in this case you can use all 3. The type of image would be real as those light rays are converging. The orientation is inverted compared to the object, and the size you can see is a little bit smaller. If you want to calculate those values, you'll find the distance to the object is 45 centimeters, and the height of the image is negative 14.4 centimeters. Again, that negative tells you that it's pointing upside down, or is inverted. Example 12. Where the object is right at the focal point, follow your rules, parallel to the axis, and then through the focal point. And then light rays that travel straight through the center are unaffected. So if you draw that perfectly, you should see that those rays are traveling parallel to each other. When that happens, no image can be formed. Example 13. Parallel to the axis, and then through the focal point. And I'm going to use the second rule just for fun here. I'm going to go through the focal point and then parallel to the axis. Now if you draw this one perfectly, it should end up right at 2f. I'm a little bit outside of it there. But if it's perfectly, you can see I missed the center a little bit there, and the light and a little bit on the other side. So you can see it's not perfect, but it should be, that image should be right here at 2f. The type of image is real. Those light rays are converging. The orientation inverted compared to the object. The size of that image is exactly the same because it's found exactly the same distance away. So that kind of helps us with our calculations. The distance to the image is exactly 36 centimeters, and that should be clear hopefully by looking at the distance to the object. That's 36 centimeters from here to the lens there. So same distance on the other side, and the height of the image would simply be negative 6 centimeters because it's same height but just pointing down for negative. Last example is a concave lens. I'll do one example like this, and then I'll leave the last one for you to try on your own. So the same rules apply. Just remember to leave your ruler where it is to sort out the diverging light rays. So we're going to draw a line that goes parallel to the axis, and then remember this is a diverging lens, so the light ray is going to be bent up. But in order to find out which angle, you have to line up your ruler with the focus point on the same side as the object. So my light rays are going to appear to come from over here, but actually be leaving the lens in that direction. The other rule that I'm going to use is light rays traveling straight through the center of the lens will be unaffected. So I'm going to draw that one straight through the center. And your eyes on the right side of this lens would think that that image was being made by light coming from the same side right over here. So a couple things. Notice that the image is going to be a virtual image because the light rays are diverging on the far side. The orientation, it is in the same upright position as the object, and the size, it is a little bit smaller. If you do the calculations, you'll find that the distance to the image is negative 6.15 centimeters, and that negative is indicating that it is on the same side as the object. The focal length will also be a negative value, negative 16 centimeters, and that's also because the focal length that you use to line up for the image is also on the same side as the object.